Okay. Which is the topic now? Rotation motion, right? We are continuing.
No, sir.
Sir, acceleration of center of mass.
Center of mass, yesterday we finished. Then we got the formula R1 is equal to minus R2. Up to there we finished, right? Acceleration of center of mass. Acceleration of center of mass we finished.
No, they want to start that.
We have to start. Okay. Acceleration of center of mass. Right now. So we know, just a minute. Velocity of center of mass. Velocity of center of mass is equal to m1v1 plus m2v2 divided by m1 plus m2. Okay. Then here m is equal to m1 plus m2. Therefore, VCM is equal to m1 v1 plus m2 v2 divided by m. Then m into VCM is equal to m1 v1 plus m2 v2. Yeah, m2 v2. Now m into d by dt of VCM. Okay, is equal to m1 into d by dt of v1 plus m2 into d by dt of v2. Okay, then m into acceleration of center of mass is equal to m1 into a1 plus m2 into a2. Okay, then ACM is equal to m1 a1 plus m2 a2 divided by m. ACM is equal to m1 a1 plus m2 a2 divided by m1 plus m2. Same like this one. Velocity also, see, just a1 is replaced, v1 is replaced by a1. Okay, finish it. When you complete, please let me know.
Sir, completed.
Completed.
Sir, wait,
Just a second, sir. Just a second.
Sir, wait, sir. Wait, sir.
Sir, wait, sir.
Okay, okay.
Yes, sir.
Yes,
Finish.
sir.
Okay. Now, law of conservation of linear momentum of center of mass. Law of conservation of linear momentum of center of mass. See, we know conservation of linear momentum of a body. When there is no external force acting on the body, its linear momentum remains same. Same thing is applicable for center of mass also. As long as no force, external force acting on the center of mass, its momentum will not change. I told you this example of ruler. See, when you are trying to, did you try this experiment? When you try this finger to bring closer here, automatically the either side of the center of mass will adjust, but center of mass will not move as long as a force exerting onto it. Similarly, suppose this firework you can see. If you, send a, fire cracker, it just move upward. Move upward and stops for a moment. Then it explodes. Then you can see equally to all the sides fragments are thrown. That's why it's forming a spherical shape. So that center of mass will not remain, will not be changed. That will remain same. Okay. And another example, suppose here you are throwing a bottle. okay, along this track. So bottle will come and fall here. But if you throw this bottle rotating at one end, bottle will rotate like this. Bottle will rotate like this. Okay, look here, bottle first it will go to this way, center of mass, then it will turn this side like this, see, then it will go to this side. This bottle keep rotating, okay, like this. But center of mass of the bottle always go in that trajectory. Center of mass will not be affected. Similarly, if we send a shell, for example, first one shell we are throwing in this way. Track A, B, C. Second time the same shell, suppose exploding at this point, then its fragments will go to different places, but center of mass will travel along the same trajectory, ABC. Then one more example, just now. See, we are telling about the Earth moving around the sun in elliptical orbit. Actually, there we are observing center of mass between Earth and the moon. So this is the way moon moving around the Earth. Okay, show you that. Suppose this is the sun here. This is an elliptical path. Moon is not a sun is Earth is not exactly on this orbit. Earth is here, for example. Then around here, moon is rotating. So its center of mass falls on this orbit. When moon come inside, naturally Earth will go outside. Is it clear? Like this. And moon is here, Earth will be here. So it keep on rotating. So that center of mass always in the orbit. This center of mass we are studying for this orbiting. Otherwise, it's very complex motion. Earth is spinning, moon is spinning. And moon moves around the Earth. And that center of mass comes on the orbit of the sun. And when these are moving, isn't it? Moon and sun keep moving in and out. And center of mass keep moving along the orbit. As long as some external force acting onto it, that center of mass will not be affected. Is it clear?
Yes, sir.
Yes, sir.
Right now. If there is no external force acting on the center of mass, if there is no external force acting on the center of mass, if there is no external force acting on the center of mass, its linear momentum remains constant. Its linear momentum remains constant. Its linear momentum remains constant. Example, a shell is fired along a trajectory ABC. A shell is fired along a trajectory ABC. If it explodes at B,
Sir, can you repeat the example?
a shell is projected along the trajectory ABC. If it is exploded at B, its fragments are scattered in such a way, so that the center of mass continues its motion along the same trajectory.
Sir, its fragments
Are scattered in such a way so that its center of mass continues to travel along the same trajectory. Then if you want, you can draw this diagram. Is it over?
No, sir. No, sir.
No, sir, only the diagram.
Sir, when the shell is exploded, sir, so there won't be any object, yeah.
What is that?
So when shell exploded, so there won't be anything left.
Sharpnel is inside this shell. Some little objects are inside there to damage the.
See, if this is scattered, they move in such a way that center of mass, you see, they move apart like this, okay? So that center of mass will be along the same direction. That way only these fragments will move. Clear?
Okay, sir, got it. Yes, sir, yes, sir.
Finish, sir.
Next. Center of mass of regularly shaped bodies. Center of mass of regularly shaped bodies. Regularly shaped homogeneous bodies. Okay, it should be same material. For example, if it is a disk, we can balance the disk with a small pointed end at the center, right? This point.
Yes, sir.
So that is the center of mass. Okay. If it's a ring, it is a disk. Okay. If it's a ring, then where is the center of mass?
In the middle.
In the middle, right, sir?
Center itself, at the geometrical center, there is a center of mass. It is not necessary. Center of mass is within the material. Center of mass can be outside the material also. See, anywhere on you try to balance it, it will never balance. But if you're keeping a small rod across it, it will balance at this point. Isn't it?
Yes, sir.
So center of mass is not necessarily within the material. Center of mass can be outside the material and within the, outside the material. Okay, example, the ring. Clear? Next one.
Could you
Hollow
explain
sphere.
the example, sir?
Which one?
The ring example.
Ring example, hollow sphere is the example. Hollow cylinder is an example. It is not within the material. Clear? But at the center of the material. Any doubt? Similarly, square.
No, sir.
If you're taking it's at the center of mass, right? But if it is not homogeneous, it is heterogeneous. For example, one material is made up of copper and one material is made up of wood. Then center of mass will not be exactly at the center. Center of mass will shift into where more mass distribution. That means more denser region. Where the more denser region comes, center of mass will shift to that point. See, this is more denser region compared to this region because this is iron or metal, anything, iron. This is wood. That means this region is more denser. So center of mass will shift to this point. Is it clear?
Yes, sir.
Yes, sir.
So write down. For a homogeneous, regularly shaped bodies, center of mass is at its geometrical center. Center of mass is at its geometrical center.
Sir, for homogeneous.
Regularly shaped bodies, center of mass is at its geometrical center. Center of mass is at its geometrical center. But if the material is heterogeneous, Then center of mass shifted to the denser region of the material. Center of mass is shifted to the denser region of the material. Center of mass is not necessarily within the material. Center of mass is not necessarily within the material.
Sir, excuse me, sir. If it is heterogeneous,
Either you tell me to wait and ask me to repeat. When I'm speaking about one sentence, you don't pull me back to the previous sentence.
okay, sir. Sorry.
Is it clear? That will be creating problem for me and others also.
Okay, sir.
So either you go along with me or tell me to wait or tell me to repeat on the spot. When
Okay,
I'm
sir.
speaking one sentence, don't ask me the previous sentence. Then it will be a problem for me.
Okay,
He
sir.
said you
Yeah.
can check the charts. It's in the charts, the paragraph.
Because even when I'm repeating, the sentence will change. You know, the grammatical, the way framing of sentence will change. So students have to keep cutting and writing again. Okay, tell me now, what's your doubt?
If
If
the
you're slow, I'm
material
ready
is
to go slow. But you
heterogeneous,
tell me, what is that?
if the material is heterogeneous,
Then center of mass is shifted to, the denser region of the material. Center of mass is shifted to denser region of the material. Have you written?
yes, sir.
Next paragraph. Center of mass is not necessarily within the material. Center of mass is not necessarily within the material. Center of mass is not necessarily within the material. Example, in the case of a ring, center of mass is at its geometrical center. Center of mass is at its geometrical center. For example, in the case of a ring, center of mass is at its geometrical center, but not within the ring, but not within the material of the ring. Then you can draw this diagram. Center of mass is a geometrical shape. Here this is iron. Okay, denser region, this is lighter region, wood. So center of mass is shifting here. Is that over?
Sir, can a body has two center of mass?
No. Is it over?
Yes, sir.
Sir.
Then center of mass of irregular shaped bodies. Center of mass of irregular shaped bodies. Center of mass of irregular shaped bodies. So for example, we have a plain lamina. Lamina means a sheet like this, a lamina. Irregular shape. Irregular shape. To find out its center of mass, what's the technology we are doing here? First, you make a hole at this point and mark it A, and one this point B, and here one point C. 3 different corners. Then make a hole. Just a minute. Then you see, this we can suspend it. Okay, just suspend it at one point. For example, just suspend it here like this and allow to rest freely. This one finally it will come to rest. While resting, it will rest along that center of mass only. Along the weight only it will come to rest. Isn't it? Tell me.
Yes, sir.
Yes,
Yeah,
sir.
it will come to rest. Then along that weight it will come to rest actually. Now, plumb line you have to take. Plumb line. Plumb line means there is a long string and at that tip there is a weight. Heavy weight will be there. Actual shape is like this. Usually masons they use it. See, like this. Long string and a weight at the bottom. That will be always vertically down it will act. So like this. Can you see this plumb line which I am using here?
Yes, sir.
Like this. Now what you have to do, suspend this on a vertical plane like this. Okay, suspend this and hold the plumb line along with it. See the plumb line passing through this wire. Can you see that?
Yes, sir.
Yes, sir.
Draw a line along with it. Then take the another corner. Same way repeat. So all the time draw the line passing by plumb line. That intersecting point will give you center of mass. Okay, that means first is suspend it at A, then you will get a line like this. Then take B and suspend, repeat the experiment, you will get a line like this. Then suspend C, you will get a line like this. Suspend C, okay. Then this point will be center of mass. This is the way center of mass of an irregular shaped body we can calculate. Is it clear?
Yes,
Yes.
sir.
Draw the diagram.
Sir, is it necessary we have to do this with 3 corners only? We can do with 2 as well.
Any 3 corners you can use.
Can we take it with 2?
2 also we can, but usually the experiment is done by 3. That's all. Because to make sure, if you can take more than 3 also, no problem. But make more.
Okay, sir. Thank you, sir.
Have you drawn diagram?
Yes, sir.
Right. Put 3 holes. Put 3 holes on the lamina. On the lamina at A, B, and C. At A, B, and C. Suspend the lamina on a support. Suspend the lamina on a support. And allow it to move freely. And allow it to move freely. When it comes to rest, take a plumb line. Plumb line. I told you this will be like this. Take a plumb line and hold it at A. Take a plumb line and hold it at A. Take a plumb line and hold it at A. Then draw a line. Then draw a line along the direction. Draw a line along the direction indicated by, along the direction indicated, along the direction indicated by the plumb line, which is passing through center of mass. Repeat the experiment. Repeat the experiment for the holes B and C. For the holes B and C. Then intersecting point of these lines, intersecting point of these lines, intersecting points of these lines, intersecting points of these lines gives center of mass.
So, but such a structure doesn't have any defined corners. How are we going to determine
Any
corners?
three corners you can choose, but maximum distance, when you're taking ABC, the distance between ABC make maximum.
Okay, sir.
That's all. Okay, right. Next, some conceptual question can be asked from here. Suppose this is a pendulum. Okay, pendulum. We know there is a long string and there is a spherical body at its bottom. Okay, it's not necessarily spherical body, it can be any shape. Say for example, here I am keeping a vessel like this. Like this. Okay. Now, wait a minute. I'll keep a bucket of water. It will be like this. Now we know usually center of mass will be on bucket of water, like this full of water. Somewhere here it will come. No center of mass.
Yes,
Yes,
sir.
sir.
Because this is, tapering here. If it is equilateral triangle, we can say it's at center. Now it is tapering. We'll draw a little more tapered. Right. Like this. So somewhere here it will come. Now time period of oscillation. If this is oscillating, time period of oscillation 2 pi root of L by G. L is the length from center, this one, suspension to center of mass. That is the length. Now, this bucket is leaking. Suppose a hole I am making here, then water will be leaking. Then what will happen? This water level will come down, right? Isn't it?
Yes, sir.
Then center of mass will lower. Agreed?
Yes, sir, it takes more time.
When center of mass is lowering, effective length will increase. When effective length increase, time period increase. So that pendulum becomes slower.
Sir, how will the length increase?
When water decreases, center of mass.
Initially, this is full of water.
Yes, sir.
Somewhere here, center of mass will come, right?
Yes.
When water is leaking, water goes down, right?
Yes, sir.
Then more mass distribution come this area.
Yes.
This is almost empty.
Yes, sir.
Isn't it? Then what will happen to center of mass? Will it be same place?
No, sir, it will come down.
it will come down. So effective length will increase, right?
Okay. Now got it, sir.
Then time period will increase. Okay.
Yes, sir.
Finally, this water will completely empty.
Yes, sir.
Then T is equal to 2 pi into root of L by G. So initially, say this bucket is like this. Okay. Initially center of mass here. As the water drains out here, as the water drains out, this center of mass will come down, isn't it?
Yes, sir.
Then time period will increase. After that, this water will, beyond the limit, water goes down, right? Okay. When it reaches here, then this bucket decides center of mass because amount of water is very less. Then what happens? Center of mass will come back again. So once complete water is removed from here, drained out, center of mass will come to the original place, right?
Yes, sir.
So first length increases, then it come back to the original place. So time period also first increases, then come back to the original place. Okay, this is one question usually they ask. And another one, if they use here ice in the form of a sphere, one ice we are keeping, what will happen to time period? From suspension to center of mass. See, this ice melt from all the sides at the same time. So center of mass remain same. Therefore, time period does not change. Okay. So these kind of questions can be asked. Next, torque.
Yes, of course.
Torque or moment of force. Torque or moment of force. This in cross product we have studied in detail. In cross product explained. Now I will go only that final explanation. Okay. Look here. Torque. Torque or moment of force. It is a rotational effect of force. That means here we have taken an example. A door handle is kept at the free end because it's easy to open. Because torque is force into perpendicular distance between fixed point to line of action of force. This is all we studied in cross product when we studied. This is the diagram for it. For example, this is an object. This is the fixed point. This is the lever, say spanner or whatever it is. Here we are exerting a force. We are exerting a force. Now we can make a perpendicular distance for it. See, this is a dotted line. We extend it to a perpendicular distance. Okay, perpendicular distance. See, perpendicular distance from fixed points to this is line of action of force. It's a dotted line. Okay, this is line of perpendicular distance between fixed point to line of action of force. And here also this is a dotted line. This is dotted line. This angle is phi. This angle also phi. This is R. Okay, this side is N. So this ON is nothing but opposite side of this one. That means R sine phi. And we have written torque or moment of force is equal to force into perpendicular distance between line of action of force. And we have written RF sine theta or vector form R cross F. Okay. R cross F. And torque is found to be perpendicular to R and perpendicular to F. This can be direction, can be obtained by Fleming's, not Fleming's, Maxwell's right-handed screw rule, or we were using this one IJK. You remember this principle we were using there. I cross J is K, that method we were using. This way we found direction of the torque. Every cross product has a property. Torque is perpendicular to R and perpendicular to F, but R and F are not perpendicular. This example we have studied in detail in cross product. That's what I'm not going very detail about it. There we took the example. This is a spanner we kept here and we exerted a force. So this nut fastener came out here. Opposite side, if you're doing, that will go inward. Is it clear?
Yes, sir.
Drop the diagram. Moment of force.
Sir, moment or momentum?
Moment of force we are doing now. Have you finished moment of force here? Did I teach you moment of force?
No, sir.
No,
Sir,
sir.
loud. Is it momentum or moment?
Moment.
Oh,
Moment.
okay, moment.
Moment means here in this, moment means there are many meaning in English, but here moment of force means rotational effect of force. Moment of momentum means rotational effect of momentum. Moment of inertia of a rotating body. So moment is always here in this physics, it's indicating rotation. Okay. So first let us study moment of force. Then next topic we will study moment of linear momentum, then moment of inertia. These are the three topics we have to finish here now. Now this is moment of force, means rotational effect of force. For example, a nut, if you want to unscrew, you have to take a long spanner. So it's force, perpendicular distance. These two factors decides this rotation. So this can easily rotate if the point P come to this N. If this position, if you are exerting, maximum force, maximum rotation effect you will get. As this increasing, say perpendicular distance decreasing. This all we discussed before. Again it is turning, say perpendicular distance decreasing. Once it is in this place, it won't rotate because no perpendicular distance. Clear? Do you follow this? Did you understand this? Oh, right now. So moment of force can be defined as moment of force or torque can be defined as the product of force into perpendicular distance between the line of action of force. That means force acting at the point P, we are extending that action. Perpendicular distance between line of action of force from the fixed point. Perpendicular distance between the line of perpendicular distance of the line of force, right? Not of between. Perpendicular distance of the line of action of force from the fixed point. Perpendicular distance of the line of action of force from the fixed point. That is a torque. Then draw diagram. Then from the diagram, force into perpendicular distance is r sine phi. This can be expressed in vector form. It is a cross product. Have you written?
Yes, sir.
Your torque is perpendicular
Yes,
to
sir.
R, perpendicular to F. R and F are not necessarily perpendicular. Torque is perpendicular to R, perpendicular to F. And R and F are not necessarily perpendicular. The direction of the torque can be obtained by Maxwell right-handed screw rule. Maxwell right-handed screw rule.
So the direction of torque after that?
Can be obtained by Maxwell right-handed screw rule. Now, look here. Suppose if this is a center point fixed and the equivalent opposite forces at the two ends. If two equivalent opposite forces, right? If two equivalent opposite forces acting with respect to a fixed point at the center. If two equivalent opposite forces acting with respect to a fixed point at the center, then torque can be obtained as follows.
Sir, could you repeat once again from starting?
If equivalent opposite forces acting with respect to the center as shown in figure, then torque can be written as, look here, written as follows. Okay, so this is F, this is the perpendicular distance for it. See, perpendicular distance. This is also perpendicular distance. So this is A, B, C, D. Okay, so with respect to O, this is the torque acting, moment of force. Okay, with respect to O, that is nothing but F into perpendicular distance is OB. Similarly, this with respect to O, at this point, it will also having a rotation like this. F into OA. So net torque is equal, both are in same direction, right? So we can say FOB plus FOA, FOA, or F into OB plus OA, or F into OB plus OA is BA. Okay.
Sir, should we draw the diagram?
Yes, yes. From the diagram we are explaining. So net torque F into BA. That means magnitude of one of the forces in this case. Magnitude of torque in this case. Magnitude of one of the forces. That means if this is 10 Newton, this is minus 10 Newton, you have to take just 10. That's what magnitude of one of the forces into perpendicular distance between line of action of forces. Magnitude of, this one I'm writing again, magnitude of one of the forces. That means if this is 10 Newton, this is minus 10 Newton, take 10 Newton, that's all. Into perpendicular distance, that means AB. Perpendicular distance between line of action of forces.
The torque equals magnitude of one of the
Forces. That means here 10 Newton, here minus 10 Newton, here you have to substitute just 10 into perpendicular distance. Is this over?
Yes, sir.
Just a
Yes,
second.
sir.
Next, the problem. Numerical. Huh? Already we did this numerical in cross product. Still one
Sir,
numerical.
can you go back, sir, please? Thank you, sir. Thank you. Sir, finish.
Right. Now numerical. The component of the force acting on an object is. The component of the force acting on an object is vector F is equal to 6I plus 7J plus 8K Newton.
Can you repeat, sir?
The component of the force acting on an object is F is equal to 6I plus 7J plus 8K. And position vector R is equal to 3I plus 7J plus 8K. This is Newton, this is meter. Calculate the torque acting on the object. So torque is equal to R cross F. It's not F cross R, R cross F. Then torque is equal to, you have to put 2 lines here, I, J, K. I is 6, J 7, 8. Sorry, it should go reverse. First R, okay, 3, 7, 8. Otherwise, you will go wrong. R cross of 6, 7, 8. And you are right, I into this cancel, 56. Minus 56 will come, right? Second component minus J into this gone, this gone. 48. J plus K into these two cancel. 42. So your final answer will come. Torque is equal to I into, this is cancelled, 0, minus
Plus 24.
minus plus 24, right? 24J. This will be minus 21K. 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 If you want magnitude of this, you have to take square root of 24 square plus 21 square. That will be the actual value. Unit Newton meter.
Sir, it should be minus 21 square, right?
Minus 21 square means 21 square only will come, right? Minus 21 square and 21 square answer will be same, right?
Yes, sir. Yes, sir.
Can I continue?
Yes, sir.
Yes, sir.
Next, expression for torque. in Cartesian coordinate system. In Cartesian coordinate system. Expression for the torque in Cartesian coordinate system. Okay. Draw diagram. This is X, this is Y. Have you drawn that? Oh. Draw when I'm drawing, okay? Now here, this is the position vector R vector R. At this point, this makes an angle theta with x-axis. At this point, we are now no need of this one because we are not taking theta as value. Now here, a force exerting here. Force F. Theta and d theta, yes, take theta. Theta, okay, right. Now here, a force exerting. What will happen to this R? Will it remain there? It's fixed here. What will happen to R? Will it travel in this direction or will it rotate?
Rotate, sir.
It will rotate.
It will rotate.
Yes,
This is origin O. With respect to origin, this will go in an arc, isn't it?
Yes, sir.
Yes, sir.
So we have to mark that arc there. So this is the path. It goes. Here, will it go downward or upward?
Sir, downwards.
Downward. Let us see. These are the component of the force. This is Fy. This is Fx. Now tell me which side it will go. This way or this way? Downward or upward? Now.
So it will go upward.
Sir, upward, sir.
Because Fy is
Upward,
more.
sir.
Because this angle is more, right? So Fy is more. Isn't it? Yeah.
Yes, sir.
Yeah. If this is more, it will come to this side. If it's exactly 45 degrees, it won't move. Now you see, this Fy and Fx two components. Now look, corresponding to this R, okay, you can put a dotted line here. This is X, right? For R, this is X. We can say IX. That you don't mark, just understand. This is IX, right?
Yes,
Yes.
sir.
Now this side will be, don't mark it, just listen. This is
I1.
IX, JY,
JY.
right? JY. Agreed?
Yes,
Yes,
sir.
sir.
So for example, this is 6 or 8. This is 6. For example, I'm writing, right? Now this will tilt. You said this will shift to a new point. Suppose
Correct.
this one shifted to a new point, this point, okay? So initially this is P, now it is Q. Now what happened to this position vector, this one? X shifted to a new point, right?
Yes,
Yes.
sir.
X shifted to here, say for example 6. And Y shifted to this point. Y shifted to this point now. That become 8, isn't it?
Yes, sir.
Yes, sir.
Now when P shifted to Q, we can say displacement in this direction. P shifted to Q. When P shifted to Q, along x-axis, the displacement is dx, right? Isn't it?
Yes, sir.
This is say dr. It is going from P to Q. Then x-axis shifted by how much? Dx, right?
Yes.
Yes.
Sir.
That means 2, for example. And y-axis increased by 2, right? So this is y-axis that we can mark as dy, isn't it? Any doubt?
No, sir.
No.
No, sir.
The dx and dy will always be equal.
Not necessary. Not necessary. It's not necessary to be equal. Okay. Yeah. So these are not just for your reference. I have marked here. Just to keep in mind that. Any doubt in this?
No, sir.
In this
sir.
diagram? Oh, okay. Now OP is R. Okay. Then what is OQ? It's a vector addition, triangular vector addition. OP plus PQ will be equal to OR, right? Triangular vector addition.
Yes, sir.
OP plus PQ. Adjacent side of a triangle taken in order. Then third side in the reverse order will give you resultant, isn't it?
Yes, sir.
So OQ we can mark as vector R plus vector dr. Agreed?
Yes, sir.
Yes, sir.
But dr we can mark as I dx plus j dy, right? Dr.
Yes, sir.
Yes, sir.
Square root of dx squared plus dy squared will give you this dr. Okay. Your angle turned is d theta. Any doubt?
So can you explain about the R1?
Yes, sir. I also didn't get that.
R1 is R plus dr.
Yes, sir.
Triangular law vector addition. OP plus PQ is equal to OQ, right?
Yes, sir.
That's all. So OP is R. PQ is dr.
Yes, sir.
The resultant is R plus dr. Triangular law vector addition. What clarification you want more about it? Tell me.
No, sir. Got it, sir. Thank you.
Now, right. Let us consider a position vector R. Let us consider a position vector R. When a force applied to the point P, when a force applied to the point P, the object is displaced to PQ. The object is displaced to Q.
Sir, sorry, sir. Can you say from the starting again?
When a force F is applied at P, the object is displaced to Q. Making a small displacement dr. Making a small displacement dr. Then from figure, the work done for this displacement can be written as work done for this displacement can be written as dw is equal to F dot dr. dw is equal to F dot dr. Dot product, right? Force into dr. Any doubt? Do you have any doubt in this?
No, sir.
Work done for this displacement is dw is equal to F dot dr. But here the problem, force has two components. Dr also having two components. Okay? Therefore we can write F is equal to here. F is equal to here. F is equal to Fx, Ifx plus Jfy, and dr is equal to Idx plus Jdy. Any doubt? Do you have any doubt here?
No, sir.
No, sir.
No. Therefore, dw is equal to Ifx plus Jfy dot Idx plus Jdy. Now it is dot product. We know I dot I will be there, I dot j will be cancelled. J dot I will be 0, J dot j will be there. So dw is equal to fx dx plus fy dy. Equation number 1. Okay. Any doubt?
No,
No,
sir.
sir.
Then from the figure, r is equal to x is equal to r cos theta. X is
Sir.
equal to r cos theta from figure, which is x. This is x. R cos theta. Any doubt?
No, sir.
Sir, I have a doubt, sir. Sir, how delta R equals Idx plus Jdy?
This dr. This one.
Yes, sir.
This is dr, right?
Yes, sir.
What is this x-axis?
Dx.
What is this y-axis?
Dy. Yes, sir.
D. Isn't it?
Yes, sir. Yes, sir. I got it.
Then square root of dx square plus dy square will give you dr magnitude.
Yes, sir.
Now x is equal to r cos theta. See, this is r. OP is r. Then x is r cos theta. And y is equal to r sin theta. This is y. R sin theta, opposite side. So this is opposite side and this was same. Okay, r sin theta. Now dx by d theta is equal to r into minus sin theta. That's a formula. Dx by d by d theta of sin theta is equal to cos theta. D by d theta of cos theta is equal to minus sin theta. That's a formula, okay? So here d by d theta of x is r into this become d by d theta of cos theta. That become minus sin theta. Any doubt? Do you understand this formula?
Yes.
Yes.
Hmm? Did you understand this formula?
Yes, sir.
Yes, sir.
Similarly, then write dx is equal to r sin theta d theta. Similarly here, dy by d theta is equal to r into d by d theta of sin theta cos theta. Therefore, dy is equal to r cos theta d theta.
So it should be minus r sin theta d theta, no?
Yes, sir.
Yeah. Then dx is equal to minus r sin theta is y. So y d theta will come here. Okay. R sin theta is y. Y dy minus y dy. Dy